Today we're going to be talking to you about quantum dot ELISA assay modification. This is a grant term project for EH0301 for UAH by Ivan Whitehead. So first off, what is an ELISA? This is important because it's really what we're going to be modifying here. So an ELISA is an enzyme-linked immunosorbent assay. This basically is where we take an enzyme and connect it to an antibody-antigen reaction, and we can make it fluoresce based off of the amount of enzyme we have, solution we have, and the number of antigens that are connected. We do this by connecting the enzyme to the antibody that we're testing to, or to a secondary antibody that we're testing is actually connected to the antigen. This allows us to actually check based off of fluorescence of an enzyme substrate interaction, as well as making sure the antigen antibody test is actually going on. So we use enzymatic induced fluorescence of a substrate where we introduce a compound that the enzyme is designed to turn into a fluorescent compound at the end after everything is bound, so we can see how much of the enzyme is bound based off of a standard test measurement based off of time. ELISAs are normally used for allergy testing or other immunotests that are required to actually be able to make sure that somebody doesn't have a really bad reaction or a problem with whatever medication they might be going on to if it has been shown that they might need to have this kind of test done. So, the standard path and how we create a ELISA, this ELISA diagram is for checking on cancer and the immunoreaction of cancer cells in our body. So we first take our antigen, which here is the VEGF, and we block it using a non-amphoteric plastic layer to allow only the opening section of the where the antibody should react with the antigen. So we can only have one antibody-antigen reaction at a time. Then we add our first antibody, wash away all the extras, then add in our second antibody that has the enzyme, as you can see with the E, and then after washing away all the extras, we add the substrate, which allows for our color development, and we see it change from white to blue. That's the standard ELISA test, and that should function for any antigen that we have as long as we follow the same pattern. But we have different real kinds of ELISA tests. So you have the direct, the indirect, and the sandwich. So the direct is utilized for just you have the antibody-antigen complex and it forms together and we test that the antibody is actually connected there. That's how we do that. Second, we have the indirect, which utilizes a secondary antibody to connect with the primary antibody to make sure that everything is actually connected initially, and we can actually ensure that the second antibody is actually present on the primary and not having some secondary interaction. Sorry about the mic. Mic is falling. That should fix it. But as you see on the right, we have the direct, indirect, and capture assay, also known as a sandwich assay. So the difference between the sandwich assay and the other two is we have a capture antibody that actually is holding onto the antigen primarily, and that's how we initially sink it into the plastic, because some antigens don't like binding under a plastic layer, or they can shift around in a plastic layer and it's not really useful for us. So we have to bind it to an antibody primarily, and then we can proceed with an indirect assay to make sure that the antigen is actually connected to the secondary antibody instead of just having the secondary antibody connect to the capture antibody. And so we have to use 3 different antibodies there so things don't interact. So with this, we also have something called a competitive ELISA. This is more of an in-batch piece. As we see, we have 2 different antigens actually exposed, the blue and the red. We will have enzymes that are only for the red, and then we see some of them are floating around and some of them are sunk into the plastic because that's where they bind. When we wash in step 3, all of those enzymes and antibodies that are connected to the reds that are not sunk to the ground will get washed out with the liquid before we add the substrate for the change in color. This really allows us to do larger batches of stuff and allow just the antigens that bind to the plastic themselves to be able to sit there, and then from there we'll have a color change based off of what is bound. This utilizes more antigens and more antibodies, but is also a much quicker method. And its bonuses are that it is fast. You only have one wash, but the weaknesses are you actually run through more of your antigen and you run through more of your antibodies and enzymes faster than any of the other methods. So, before we start talking about how we can modify the ELISA with quantum dots, I first need to explain what quantum dots are. Quantum dots are nanoscale particles of semiconductor material that have optical and electronic properties that differ from large-scale materials due to the quantum mechanics. That is a fairly complex definition, and really what we're working with is a nanoparticle that is designed to fluoresce through mechanical means and quantum mechanical means instead of chemical means like an enzyme-substrate interaction. This is more of utilizing the properties of a semiconductor material as itself, where we utilize the principle of electron shifting from shell to shell based off of semiconductors, which are able to shift that. They're able to shift the actual amount of energy you need up or down based off of the actual binding we're going to be using. We're going to be using indium potassium for a lot of my tests, and that's going to actually create a shortening of the gap between two shells, more easily allowing for fluorescence to actually function in a standard way that quantum dots are actually built. So we can have a more consistent fluorescence from a wider range of light. So the major structure of quantum dots is we have three major pieces. We have our core, which for us is indium. Then we've got our shell, which is our phosphorus. And this will create its basic ionic cell structure. That is what's allowing for the light to come in, the electrons to shift, and the different photon to be produced from the electronic change. And then we've got a protective shell in this quantum dot. We use a protective shell in this structure because it is required due to interactions with physiological serums causing quantum dots to either break apart or to be negated or dampened. Utilizing a biotin or a bovine serum albumin or an amphoteric plastic shell allows for this blockage to not form as easily or to be inhibited completely. So this is its real strength of quantum dots. Quantum dots can take the same color of light, which in this example is 450 nanometers, which is a solid blue light. And based off of the nanometer difference in dot size and the difference in the shells of the different layers, we can produce different colors of light from one large spectrum of light. So in the example, we have blue light coming in, which if you see that vial, the far left vial is the blue light coming in. And then as we proceed to the right, the increase in nanometer size causes a physical change in color that we can see. And this also means that we can measure this physical change in light, which we see over on the right side, where we see as the nanometer wavelength increases, for each different color of quantum dot, we have a different peak on that Gaussian curve to where we can identify that this is this quantum dot, which means using fluorescence, we would also be able to go, this is this antibody-antigen reaction, meaning that if we were to do batches of this without having to wash anything, we would be able to identify the number of quantum dots inside the solution that we gave, just based on concentration. And then after washing, we'd be able to tell us, based off of the fluorescent strength afterwards, the number of quantum dots that stayed connected to the lining of the plastic that we had, or similar to the competitive ELISA, how much actually sunk to the plastic and actually stayed around. And you can tell the concentration of each antigen if you wanted to test multiple antigens at the same time, because now we have fluorescence that doesn't overlap in its absorbance spectrum, because it all absorbs the same color of light. We use the same color of light. We get different readings. We don't have to worry about overwriting spectra. So the major structure that we're looking here is twofold. The centerpiece, the CDTN, the cadmium-tellurium antibody connector, is really the structure that we're looking for how we're going to bind our antibody to our antigen using an avidin protein binder and a connector on a DBSA and biotin shell. So the DBSA is going to be the major blockage protector. It's going to be our protective shell, where the biotin is really where we're going to be binding stuff. You can sub out biotin for other binding proteins, but the deuterated deuterated bovine serum albumin, the DBSA, is what we're going to be using as a protective shell around the cadmium selenium to avoid breakage during interaction with serums and other washes. So we don't have to worry about corona effect on proteins or other binding inhibitors. If we go to look to the left where A is, we will see a well setup where you can have different colored quantum dots connected to different antigen antibody complexes in a similar structure. And then to the right, we have an assay formatting where we have 3 columns and 5 rows of the different antigens that we're able to test and have quantum dots pass from where 4, 5, and 6 are on that chest across the film. And if they do not meet any antigens they do not interact with, they will just flow all the way through, and we'll see where they connect. And that way we can test with thin layer chromatography and other movement abilities along a strip which antigens which antibodies can connect to which antigens based off of distance and where they also are. And instead of just having to do one well at a time checking each antigen setup, we can do a thin layer chromatography pass with multiple antigens antibody complexes at the same time. Well, thank you for coming and listening to my grant proposal presentation. I really hope you can come back and if you have any questions, come back and message me. And I sure hope that all of you got to learn something extra about this, and that if you find it interesting, you would be willing to support me with my research during grad school.